G'day, by popular demand, this is me answering the practice VCE physics exam. The exam gave you the answers to the multi-choice questions on the back page. I'm not too sure whether you saw that, but the answers to multi-choice questions are there. I'm happy to go through any of them in the classroom, in the lessons that we have left, the 3 lessons we have left. So I'm going to go straight to the written section. So let me just turn straight to the written section. I've completed this. There we go. Section B. Okay. Right, so the first question is a connected body question. And they've simplified the diagram here. You can read this. I'm assuming you have the test with you. Shanna's got a tricycle. Give her little brother a ride. Mass of the trolley, the force pushing it forward. We've seen this sort of setup before. Question 1. Calculate the magnitude of the acceleration of Shanna, her brother, and the tricycle with the trailer. Now, this is the whole thing. Right? Most of these connected body questions are F equals ma questions. You're nearly always using F equals ma, but the way to get this right is to make sure you're using F equals ma for the right part. And for this, it's all of it, because you're calculating the magnitude of the acceleration of Shanna, her brother, and the tricycle, so it's the whole damn thing. The whole thing has one force of 35 newtons on it. The whole thing weighs 70 kilograms. That's the 45 plus the 25. And so you find A. Sort that out. A comes to 0.5 meters per second squared. That's easy enough. Second one, calculate the magnitude of the force exerted on Shanna and the tricycle by her brother and the trailer. So this is what's pulling her back. Right? It's the force on Shanna. In fact, I'm going to go down here. It's the force on Shanna by this. So if this trailer wasn't here, you wouldn't have that tension pulling you back. Tension is pulling her back, and she can feel it because she needs to pedal harder. And the tension is pulling the brother forward, and he can feel it because he's being forward. Right? Those two forces are the same. They cancel each other out. But to find out what they both are, they both have a value. You need to consider one of them or the other, and we're going to consider Shanna. So considering A, say it, right? Tell the exam that you're talking about the front box. It's again F equals ma, right? And the forces on Shanna are 35 in one direction and the tension in the other direction. That's why they're minus here. So for T, tension is 12.5 newtons. Next one. State the magnitude of the force exerted by Shanna and the tricycle on her brother and the trailer. Like I said, these two are the same. They're just in opposite directions. 12.5, the other one is 12.5. That's why they didn't ask. Just gave you 1 mark for stating it. Okay. In real life, Shanna finds that once she's got the tricycle and trailer moving, they travel at a steady speed. Which one of the assumptions made in model explain why she doesn't? Because in isolation, this should keep accelerating forever because the overall force on the whole thing is 35 newtons. Right? And the thing that we should, the thing that we should fix is ignoring retarding friction. If it's not accelerating, then the retarding friction would be equal to 35 newtons. So they just told us to ignore it. And it says which one of the assumptions made needs to be changed. No retarding friction needs to be changed. And because it's only 1 mark, and I just asked you the question, just answer it and that's it. It didn't say explain, it didn't say justify your answer, that's it. Okay. Question 2. All right. Projectile motion, everyone's. She runs off the edge of the pier or whatever it is, the platform, running horizontally, and she's eventually going to fall into the water. And the question is, how far did she land from the edge of the pier, from the edge of the platform? Here's how to do it. to keep vertical and horizontal separate. And it's fine to do it up here, that's fine. This is the sort of thing that you would do up here. You wouldn't do actually any of the answering of the question up here, just out in the margins. You do all that down here to make it nice and neat. However, vertically, the distance she's going to go is -8. So the vertical distance is -8. It does matter that you say minus this time. The acceleration is -9.8 equals. Her initial velocity is 0. Her initial vertical velocity is 0. She's going horizontally, so she's not going vertically at all. Right? You don't know time, and you don't know v. You don't know the final velocity vertically that she hits the water with. Horizontally, the only thing you know is she's traveling at 6 meters per second. You don't know how far she goes. That's what we're trying to find out, SH. And you don't know how long she's in the air for. The one thing that appears on both of these that's the same is time. So quite often, the key in one of these things is to use one side of this to find time and then put it on the other side and find what you're really after. And that's exactly what we're going to do here. We're going to find time here and then stick the time down there and find the horizontal distance. Okay, here's me doing it. All right, so for this, equals ut plus half at squared. Put all the stuff in, that comes to 0, so it's fairly easy, and the time turned out to be 1.27 seconds. Put that over here. There's only one formula for horizontal because there's no acceleration. It's velocity is displacement over time. I've juggled it there. And the horizontal S is part B. Lucinda would like to spend more time in the air before she lands in the water. She wants to get a bit more air time. How might she achieve this? Well, she should launch upwards as well as forwards, as well as running. Once she gets to the end here, she should go instead of just running straight off. If she bounces up, the extra height will mean she is falling from a higher spot, and she's going to take longer to fall. She's going to take a bit of time to go up as well, right? So there's extra time doing that bit before she does this bit. Okay, and that's pretty much what I've said down here. Launch upwards as well as forwards, that's the answer. And here's the justification. Having gone higher, she will take longer to fall. Perfect. All right. Question 3. Okay. This is a tennis ball being hit by a tennis racket for it. This is clearly going to be an impulse question. Whenever they've got force and time and something being hit for a certain amount of time, it's going to be an impulse question. And sure enough, calculate the impulse acting on the tennis ball during the collision. Show your reasoning. Here's the reasoning. And I want to tell you about economic communication here, right? So there's the formula. Impulse equals force times time. And force times time is going to be the area under this graph, right? Y-axis times x-axis is the area under the graph. And I counted the squares under the graph, and there were 43 squares. Now, some people would take 5 lines of writing to do that. They'd put the formula down, and then they'd say, in this case, it also equals the area under the graph in this particular graph. And in this particular graph, there are 43 squares that are either completely filled or more than half filled. Right? You don't need to say that sort of flowery sentence structure. That says everything you need. One square, one of these guys, is 50 high and 0.001 across, according to those. So it comes to a value of 0.05, and then you just go 43 times 0.05, and that's the answer, 2.15 Newton seconds. Part B. Competition tennis ball's got a mass of 0.06 kilograms. Calculate the speed with which the tennis ball takes off. Show you're working. Impulse is also a change of momentum. This is where you get the speed in it, right? mv, so it's m times the change of v. It started off not moving. They said at the beginning of the question on the other page the ball was at rest before the collision. And so the change of velocity is 0.06 v, and that comes to 2.15 because the impulse was 2.15. We just found that in part A. So solve this for v. V equals 35.8 meters per second. They told you they wanted it in kilometers per hour. That times 3.6 is kilometers per hour. I'm sure that's on your cheat sheets. It's not on the data sheet. Okay, practice tennis balls are heavier than competition balls. What effect, if any, is this going to have on the speed of a practice tennis ball if the tennis racket produces the same force versus time graph? Okay, so if the force is the same and the time is the same and the impulse is the same, right, the practice balls are going to be slower. That's the answer. That's the 1 mark. Here's the justification. The same impulse equals the same momentum because impulse equals momentum, which means that it's got the same mv, but the m is bigger, so to keep this number the same, the v is going to have to be smaller. That's the justification. All right, practice balls are always slower. Oops. Bang on a few things here. Question 4, the baby bouncer. All right. There's a baby bouncer here. It was empty and it was hanging and the spring was just sort of at a rest position. Then they put a mass of 4 kilograms in it and it lowered itself by 0.05 meters, which is 5 centimeters. Calculate the magnitude of the change of gravitational potential energy of the mass as the bouncer is lowered. Okay, well the mass was 4 kilos. Right. Gravitational potential energy is mgh. So mass of 4 kilos, g is 9.8, h is 0.05 meters, and that comes to 2.5 joules. Easy enough. Next one. Calculate the elastic strain potential energy of the stretched spring in equilibrium. Okay, they didn't tell you what the spring constant was, so you had to find that first. So when it's resting, the force pulling the bassinet up, or the bouncer up, has to be equal to the force pulling it down when it's resting, when it's not moving. In other words, kx, because F equals kx, is the strain force on a spring, equals mg. Right? Solve that. You had everything else. You had 5 centimeters, 4 kilograms, 9.8, and you get that. Right? K is 980 Newton meters, or newtons per meter. Sorry. There you go. And the question said calculate the strain potential energy. Now that you've got K, you can use this formula. A half kx squared. Again, x is the 5 centimeters that was stretched, 0.05, and you end up getting 1.2 joules. Right. Has energy been conserved in the mass spring system? Explain your answer. All right. So as it went from there down to there, did it have the same total amount of energy up here as down there, or has something changed? That's what it's asking for. In both cases, it was at rest before and after. So it wasn't moving there, and then it got down here and it wasn't moving down the bottom. So in both cases, the kinetic energy is nothing. So here's what I've done. Rest without mass. Right, at rest without the mass at the higher position, kinetic energy is 0, not moving. Strain potential energy is 0 because it isn't stretched. And the gravitational potential energy is 2.5 because we just found that out in part A. With the mass, and it went down to as low as it's going to go and stopped, kinetic energy is still 0 because it isn't moving. That is now 0 because it's down at the bottom of its traveling. And the strain potential energy, because now it's stretched, is 1.2 because we just calculated that up here. So the total energy has gone from 2.5 before to 1.2 after, so it is not conserved. It's changed. That's how to do it. All right.